Okay, we could have a few more than a third. That'd be good. All right, so this is, I guess, I don't know, it's our, what, we did 1, 2, or maybe, yeah, 1, 2, 3, 4, 5, 6. I think this is our 6th lecture. And so I will record it and I'll post it. So let me, so what I want to cover today, I'm going to do a couple things. So if we look at the syllabus, which I think I pulled up somewhere here, maybe not. Oh yeah, there. No, I didn't pull it up yet. Okay, well, yeah, let me pull that up real quick. So. Yeah, okay. Back up to S22. Okay, so let me show the syllabus here real quick. So I'm going to share my screen and we'll show the syllabus. All right, so if we scroll down to where we are here, so we're on the February 2nd, and so this week we're kind of a week behind on lab, so we'll do the bubble lab. If you want to look at lab 3, that's fine, but in lab today we'll try and do the bubble lab, or not today, but Thursday and Friday. All right, we'll also talk a little bit about we've already talked, we'll talk about the interrupts, and we'll introduce the tilt table a little bit. And I'm also going to talk about a document that I want you to spend some time looking at. I might even give you a quiz on it because I want you to look at it. So I'll talk about that briefly, but it's the user manual for the SDK for the MCU Expresso, the SDK software development kit. So we'll and I think it really will help. It's very difficult to understand. So it's fairly complicated. But I think if you just force yourself to kind of scan through it, it'll give you a little more perspective and read the parts that you can read. I think it'll give you a lot more perspective on how the software support system is set up for MCU Expresso for all the various processors and boards that they support. Because I'm going to have you, so let's dive in. So I'm going to close this. Let me stop the share for a second. Okay, I'm going to get rid of this, and then maybe I'll talk about the lab first. Okay, so let me bring up MCU Expresso. It's here. And so the lab we're going to do, so let me share again. So the lab we're going to do is lab 2. And this one uses this program called Freedom KL25Z _demo_apps_bubble. And so if you open this up, then you can, so all these examples have a doc file. And so if you open that up, there's a README text. So let's pull this up and it pops up here. And it does give you some information on it anyway. Some of it's a little goofy, but what it's going to do, it's going to print out either to your console window if you check that, or in PuTTY if you check the UART selection. It'll give you the X and the Y coordinates of the accelerometer on the board. And when you more or less zero those out, then that means your board is relatively level with the pull of gravity, or it's in a plane that's perpendicular to the gravitational axis. Okay, So we'll demonstrate that. I've actually already run it and my board's executing it now. So let me pull that up, and show you. Let's see, I've got a window here. And so let me bring this over here. Knocked around. Okay. So if I bring that over there, okay. So there's the board. So if we, and let me open up a putty window too. So I'll do this putty. So you can see it's printing out. I don't know why that didn't go right, but it didn't. Okay, so it's printing out the X and Y. And obviously, if you put it on its edge, it gives pretty big numbers. That's signing on its edge. That's the other edge, so it's minus. That's standing on its end, and that's standing with the plugs in the up direction. And then if you get it flat, you get these axes down to fairly low levels. And here you can see my LEDs off, and the numbers are they're below 70 anyway, or right at that. Okay, and then if you tilt it, then you can see it. The green comes on. If you tilt it, the x-axis, the red comes on, and if you tilt the y-axis, the green comes on. And if you get it just about right, then it's pretty good. And if you tilt it at an angle, then you get the red and the green together, which is kind of an orange. And you can change that color a little bit as you tilt it. Okay, and so that's how that lab works. Okay, so I'm going to close this. And then I'm going to shrink this down for the time being. Okay, so that's how it works, and it kind of explains it in this README file. And then the code, here's the code, and you can see it identifies a bunch of headers that it loads. One of the things, this FSL, that just stands for free scale. They put that in there because some of these boards were originally NXP boards and some of the boards were free scale boards. And where these things have to do with free scale, they preface them with FSL. The other thing that's a little confusing over here in these demo programs, some of these CMSIS driver examples, that CMSIS stands for Cortex. Let's see, I forget it as fast as I remember it. It stands for ARM Cortex Microcontroller Software Interface Standard. That's what CMSIS stands for. And I mentioned it the other day, but Doxygen is well, it's a de facto documentation standard for C++ and a number of other languages, actually. And when you pull up some of these headers, like here, you pull up, I don't know, there's a, let's see if we have a GPIO. Maybe that's down here. Under board, I think, actually. No, it's under, I guess it's under drivers. Yeah, so FSL, so free scale GPIO, C and H. And if we pop these up, so there's the header file. When you see all these things like this line here, so it uses the \* exclamation point at name driver version, and then * to close the comment out. And then it puts in this little asterisk open bracket. And then here we have the asterisk close bracket. All that, these are instructions to Doxygen to, if you ran Doxygen against this file, it would document these things. And you can actually do that. You can download the Doxygen app and you can run it against this file and it'll print out the documentation. Actually, I haven't done that yet, but I know that would work. So again, they put this in to make these really robust. Remember the grayed out areas? These apply to boards that different boards, features not available on our board. which is really nice that they're grayed out for you. So you automatically know what you don't even have to look at. Okay, so anyway, yeah, so okay, so that's that. And if we pull in the if we go, well, let's go over here. If we go into I stop share and then I share again on my other screen. Okay, so if you look in, well, let me point this out first since I'm there. So on Blackboard, if you go all the way down to, we'll look at labs here in a second. If you go all the way down to S21 video YouTube links, you click on that. Lecture 2 has interrupt start at 47:51. And if you click on that, it will actually, amazingly enough, it'll bring it up after you get through the commercial.
Dr. Morden, have you made any money yet?
I'm sorry, what? What's that?
Have you made any money off of the ads?
No. You have to have, I don't know, you probably have to hit several thousand views. I don't know. I think it's at 157 views. You have to be in the thousands and maybe even hundreds of thousands to start making money. But hey, you guys could spread the word. Maybe I could make a buck or two. Yeah, no, I haven't. I'm not in the monetary part of it yet. That's for sure. All right.
You could assign us to open it in 1,000 different tabs.
Yeah, there you go. Yeah, that would probably work. I don't know how they track that. They probably look at your IP and they know who's looking at it too. And they probably know, it's, some students doing it multiple times. So who knows? But anyway, so if you click on that, it will bring you to, for some reason, it starts here at a 47:48, but it's supposed to be 47:51. Anyway, it gets you pretty close. So it gets you to where the interrupts. If you want to watch the whole thing, you can. But I encourage you to watch, and it's from 47, so essentially 48 to 120, so 12, so 32 minutes. So it'll take you 32 minutes to watch this. This is a pretty good explanation of the interrupts. It might get a little tedious, but yeah, so watch that. And then I'm not going to talk about the interrupts because that actually covered it pretty well. Okay, so let me, all right. So what I do want to cover though, is, let's see, let me shrink this down. And I don't think it's this one. Yeah, it's the other one. Okay, so what I really do want to cover, let's see, what was that other document? No, not that one. Oh, here's the lab. Here's the document for the lab. Yeah, let's take a quick look at this. And then, so in this lab, so this is lab 2, and this is the guidance document. So it's going to be another program, and it kind of walks you through some things, and just kind of do all the things it shows you. There'll be maybe a few more things you'll pick up doing this. It kind of walks it through, and I think if you do some of these things, you'll continue to explore the IDE a little bit, and then there's a little question thing to do at the end. Okay, so do the lab Thursday. All right. Okay, that's fine. And then, so I'm good with that. All right. The other thing,
I have a quick question.
Yeah, go ahead.
Regarding the weather tomorrow, it looks like the roads are going to be the same as it was a couple weeks ago. Have you heard anything from the university?
They haven't, not yet, but I didn't really go over my email carefully today, so they may have sent something out. Did you? I'm sure you'll see it if they send something out.
Okay, thank you.
So if the roads are bad, then then screw it. Don't come in. Don't do anything dangerous. It's not worth it. Just come Friday. That's fine too. But I'll probably go in. I mean, I grew up in the Midwest. I'm used to driving in 6 inches of snow. So it doesn't bother me, even without chains or snow tires, I'm fine. And I have a front wheel drive car, so I won't have any problem. The only problem I'll have is people in front of me doing stupid things and people behind me doing stupid things. But other than that, so I'll probably go in regardless. I mean, the one thing that you can't do, nobody can drive on black ice, but we don't, I don't, I know it's going to be chilly. I think it's going to be go down to the 20s maybe. So the roads will have some freezing on them probably if they're wet. And I know we're supposed to rain. So yeah, so if it's really bad, don't come in. Even if the university doesn't say anything out, I'm never going to ding you for that. So stay safe for sure. Yeah, if it's black ice, I probably wouldn't go out either. But it's a pretty rare thing. You know, even in the Midwest, I only encountered black ice a few times where it's literally, you know, a layer of ice on the road and you can't see it. That's bad. And your car just doesn't matter what you do. If you touch the brakes, if you turn the wheel, the car may continue to go in some other direction. And if there's a brim on the highway, you'll just fall off. So I remember trying to drive on that at Fort Leonard Wood. One of my buddies' parents were here, and they were driving us around, and they were going up this little bitty incline, and the car just they were just, you know, creeping up, and the car literally just started sliding backwards. It wasn't anything they could do, and we actually hopped out of the car and you know, pushed on it to try and keep it out of the ditch. Fortunately, it wasn't going very fast, but I mean, it was just ridiculous. It was literally like you were on an ice rink. Nobody can drive on those conditions. Well, if you have chains, you can maybe make it work, but if you don't have chains, you will not drive on that.
Yeah, no. So even if you have chains, the roads will you can actually damage the roads here in San Antonio, Texas. So you're not supposed to drive them with chains.
Yeah.
By San Antonio police department standards, you can actually call their non-emergency, and they'll tell you that you're not supposed to do that. Just stay home.
Oh, that's good. Yeah, they close the interstates here in SA. Yeah, in the Midwest, you know, if you really have to drive, you put on your chains and you go. But not here. Yeah, I'll tell you one more story. I was stationed up in the high desert in California for 2 years, and my wife had one of the ladies had told her, you know, better have a set of chains in your you know, in your station wagon just in case. And so anyway, we went back to Indiana for Christmas, or maybe Missouri, I forget which. And but she had gone out and bought a box of chains and put them in the back of the car. And so anyway, so we flew in and out of San Bernardino. We flew back into San Bernardino, and it was so warm there. You know, we were in, you know, short sleeve shirts. We could have been in shorts and tennis shoes, but we probably had on long pants. But anyway, we ate at a fast food restaurant, and then we started up the hill. And the Cajon Pass goes from sea level basically to about 5,000 feet. And we just started kind of going up the hill, and they had the barricades down and they had the chains only sign out. And we literally had to pull in and put on our chains. Now, you could pay, if you didn't have chains, you could buy them there, and you could pay to have somebody install them. It only cost you $200 or $300. But my wife had bought a box, and we had them in the back of the car. So I put them on, and we went right up the hill, no problem. But they wouldn't let you go even without chains. So interesting story. Needless to say, my wife scored some points that day. All right. So what I wanted to talk about now is this MCU Expresso SDK application, well, API, whatever that stands for, application procedure interface, I guess, reference manual. Okay, this is hard reading. I'm not going to lie to you. So if any of you can read through this and you're like all over it, you totally understand everything, and this is like no problem for you, then you should be teaching this part of the class, because this is difficult for me. I'm not a big software guru. You know, I haven't written million-line programs. I've been writing software for since 1963. So it's not like I don't know how to code, but this is really, you know, this is systems level, professional code level. And so anyway, so I want you to go through this manual. So here's, if you click on the main page, this kind of the introduction, and then it gives you, it opens up a bunch of stuff, and then you get down here and there's a whole much more stuff, and these all open up. And so there's a lot to read if you want to really read through everything. You don't have to do that, but you could go through some. But here's what I want you to, let's see. I can't get back to where I was. All right, now I can't find it. Where am I? There, the architectural overview. Okay, so this is a picture of the system that MCU Expresso brings to the table to help you write code. Now you don't have to use this. You can write everything yourself and low-level stuff, but I have to tell you, their include file is not as inclusive as the include file was under Code Warrior, and so what you'll have to do is go get the include file from Code Warrior and use that instead, and you can do that. But this really helps you write the code, and it does a lot of work for you. And so what I want you to do is just take 1 hour, set it aside this weekend, and spend 1 hour reading as much as you can possibly do on this document. Now, don't spend any more than an hour unless you're just highly motivated. So this is the way this works. There's an app level up here, okay? And this app level, demo applications and driver examples. Okay, so that's what we downloaded in MCU Expresso. And when we, oh, that's funny. Let me see if it's, yeah. So that's what all these things over here are. These are all the driver examples and apps. Okay, so here are the apps, and then driver examples, and I didn't even load them all, but there are some for multiple core. There's some for the real-time operating system, and so there's several other examples that we didn't load up, or at least I didn't load up, and I told you you could skip those. So hopefully you did. All right, and let's see, is it here? Yeah. So that they sit on top of this structure. Underneath these, we have what's called the middleware. And over here on the side, we have the RTOS. So if you're using an RTOS, the RTOS is supervising all this stuff. Okay, so here's the middleware. And it's stuff like the USB device and host, the file system, crypto if you're going to use that, and then TCP/IP for an internet connection, and then your direct memory access manager. So this is kind of middleware drivers and stuff if you're going to use some of these higher level things. And then down here you have your low level drivers, and these are what are going to talk directly to your modules, configure them, run them, pass data to and from your application up here, using these structures and built-in functions. All right. So you have drivers for the SPI interface, the I2C, the UART, the analog to digital conversion. I forget what the CRC is. For the flash memory, the GPIO pins, the pulse width modulation, and a bunch of others. I don't know what FTM stands for either. All right. And then here you have the ARM core. Let's see, what did I say it stood for? ARM Cortex microcontroller software interface standard libraries here, which include all sorts of math and other things, even some AI stuff. And then here are your device headers. So these are all the output pins and stuff like that. And this is part of your Cortex, your ARM Cortex microcontroller software interface standard here. All right, so what you can read here is, so this chapter provides the architecture overview for the MCU Expresso software development kit. It describes each layer within the architecture and its associated components. So the MCU Expresso SDK architecture consists of 5 key components. So it's the ARM Cortex microcontroller software interface standard. And It has core compliance, driver specific hardware header files, SOI system on chip headers, and this CMSIS math and digital signal processing libraries. It has peripheral drivers. These are the peripheral drivers here. It has real-time operating system. There's the RTOS. It has stacks and middleware that integrate with the MCU. This is the middleware, and demo applications that sit up here on top. All right, and then you can start reading about it. And then once you move along in this, now you can read through all these various things. You can read through the introduction. You can read through driver error status. You can read through trademarks, and then you can do the API references. And if you do related pages, then let's see. Then you can slip to the API references. Okay, on these, this goes through a list of all the modules. So here's your analog to digital converter, your 12-bit SAR. And actually it is a 16-bit, so I don't know why they call it a 12-bit. Okay, the CRC is the cyclic redundancy check driver. That's why I haven't used it. And then timers, common drivers, your direct memory access, your digital microphone. I don't think we have a digital microphone on this board. Your debug console, and then here's I2C, the I2S. I2S is just a subset of I2C. This is when you punch the power button on your desktop or laptop. It's usually hooked up as an I2S device, but it's very similar to I2C. And it has if you want to use direct memory access with the I2C, it's got that. It's got the basic I2C driver. If you use it with your free RTOS, and then in master mode and slave mode. And then here you have your input multiplexing driver, your IO pin configuration, and so forth. And it goes through everything. Here's the SPI. Here's the system configuration for turning on and off clocks and stuff. But actually that gets done in this driver stuff too. So you usually don't have to mess with that. And then here's the UART, and then the micro tick timer, and the watchdog timer. So those are all the devices. Yeah, there's probably some other stuff too, but anyway, within these, then you can look through, read maybe one or two of these, maybe read, and I know there's one for GPIOs. I don't know. So see if we have, yeah. So API references. Yeah, I think that's mostly it. Oh, here's the GPIO. Yeah, GPIO general purpose. So some of them didn't show up in that description over here, but here they are over here. Real-time clock, all sorts of stuff. So just spend a little bit of time reading through some of this, and this will show you how they put things together. And what you'll see is that just read through this introduction. It does really help to look at this. Now, I know some of this will be confusing and difficult for you, and I don't worry about it. Just read on. But and for some of you may understand some of most of this. But if somebody's really all over it, let me know. Then you can help me. All right. I think what I'm going to do, since I've got about 30 minutes of video for you to look at, I'm just gonna stop here and do some questions. Oh, well, I did want to talk about the tilt table a little bit. Let me just do that. Sorry. So we'll do that real quick. All right. So the tilt table has a touch panel on top, which that's how we know where the steel ball is as it's rolling around. And how does that work? So touch panels have embedded just a myriad of technologies. This particular one is called a resistive touch panel, and it has 4 wires for its connection. Now there's a 5-wire interface. There are other versions of resistive touch panels, but the 4-wire seems to be fairly common. And I did talk about this the other day, but this is just a little more information. If you put it, if you accidentally mounted it upside down, it doesn't work very well because again, it has this top piece of glass and the bottom glass. The bottom glass is pretty rigid. The top glass is very thin and flexible. And so, and this is, and it's coated with a resistive film. So, and I don't know so in between these layers, you have this, you're kind of stuck together with adhesive. They have a connector on the edges that works as essentially an electrode. So you can actually see the electrodes. These are these colored things here. And it looks like it's just a square, but they're broken up. Like you can see this one's connected to this wire and it goes up here. And then this one is connected to the next wire and it runs here. And then this one runs all the way maybe to the edge and there's one at the top. So anyway, so they do run around here and they are connected. Some are connected to the top panel, some are connected to the bottom panel. And what you effectively do then is you have an electrode on this side and an electrode on this side and a resistive coating between them. And then down here, you have an electrode on the front edge and the back edge and a resistive coating between them. And you also have these little spacer dots. And this piece of glass is pretty stiff. And then then these are brought out through this interface here with this little flexible tail. And when the spacer and the top piece are put on it, then this connects to these electrodes up here. And so when it's all said and done, you get your 4 wires. One is connected to there's 2 essentially electrodes on the top piece and 2 on the bottom piece. So on the top, they might be left, right, and the bottom, front, back. And you have 1 wire connected to each one of these 4 electrodes. Okay. So when you touch it, you basically short this conductive film to each other at some point. And so you basically have, you have a voltage divider in both the X and the Y directions. Now, to make it work, you have to apply a differential voltage across this, ground on one end and 3.3 volts on the other. And then you don't put any power on this one. You tri-state these GPIO connections, and then you connect, you turn one of them into an input to your ADC converter. Now I just used I used 4 pins for these, and I used 2 more pins, one connected up here for the ADC for the top, one connected over here for the ADC for the top, and one connected over here for the ADC for the bottom. And so so when you power this side, then you run the ADC on the other piece of glass on one of the electrodes. And what that does, it allows you to read this voltage divider you've created here by touching. You've created a resistance on one side of your finger and a resistance on the other, effectively because of the resistive coating. And so you've divided the voltage across this with this little divider. And obviously, the closer you get to the ground end, the lower the voltage. The closer you get over here, the higher the voltage. And then your A to D converter on this panel reads it. And then you just flop that around in a matter of a microsecond or so, and you read now you power the bottom piece of glass. You tri-state these 2 inputs, and then we have an A to D converter connected up, say, to this one, and we input that value, which now does the voltage divider on the bottom because it's ground down here and 3.3 volts up here, or however you arrange it. And that way you get a reading, an X and a Y reading, and that basically tells you where your finger is. And you just do that very rapidly. Now, and you can do it. We're currently averaging, I believe we're averaging 32 readings, maybe it's 16, because the A to D converter will automatically do that for you. It will read the same input, say 16 times or 8 times or 4 or once or 32 times. You get several selections. And I think I'm doing 16. And so it reads it 16 times and average them. It may be 32, I don't remember. I'd have to go back and look at the code. But once it does that, then that's the value that it finally sets the done flag and lets you read that value. or it can do it with interrupts, or even with the DMA controller. I don't think I set it up with the DMA controller, but we might, I can't remember if we're using interrupts or not. I think we are. Yeah, we're using interrupts. Okay, so, well, maybe not. I don't remember. But I'll know when we start playing with the code. I just don't remember off the top of my head. All right. So anyway, you get that value, and then you have an X and a Y value. Now, the first thing we do is we will calibrate this, and we'll go over that in great detail how we do that. But once you have calibration values for rotational effects and scaling effects and translational effects, then you get a pretty good readout that more or less divides your x-axis and y-axis into even increments and keeps them in the right planes, no rotation. All right, yeah, so we put ground in 3.3 here and the ADC down here, and then we read that first value, the X value, and then we switch it around. We put 3.3 in ground here and the ADC on the top panel, and we read the Y value. Or maybe this is the X, I don't know, but however we do it. All right. Okay, that's really what I wanted to cover on the tilt table. So I'm going to stop with that, and then you can go ahead and watch the rest of that video to talk about the interrupts, and that'll cover what I wanted to get covered today. And then we'll do the lab. You can probably, if you have it downloaded on your laptop, you can do the lab at home because you don't need any external equipment or anything. So if you do that, then just make a little video of the app running and upload it to the TA's web address, and he can give you credit for it. Or you can send it to John Trung. All right. Any questions?
No, sir.
All right. We'll have a lot more to say about the tilt table and the cup car as we go along. And hopefully we'll with the next when we do the next app, we're gonna start from scratch and build an app up totally from the bottom up. And so I think that'll be interesting too. All right. With that, I'm going to sign off. Yeah, go ahead.
Mr. Morton, I actually wanted to show you something real quick. Give me
Sure.
1 second. I'm going to turn a little light on. I want to turn the video on.
Yeah, go ahead.
This was Tuesday.
Oh, congratulations. Yeah.
Congratulations.
That looks good.
Yep.
Looks like you got a good heartbeat too. Yeah.
Thank you.
I did a lot of those ultrasounds.
Yeah, it was funny. I was looking at it and I was like, oh, so this is how you turn it on. This is how you do this, and this is how you do that. And the doctor just looked at me and went, have you played with this before? And I'm like, no. I just could see like the buttons. They have them labeled, and then also
Right.
the way they worked around it. It was pretty fun.
Yeah, that's because you're an engineer.
Bam, welcome everybody.
Oh,
Yeah, that's great. Yeah, it's pretty interesting. Yeah, once you see the heartbeat, that so in the first trimester, the risk of miscarriage is about 25%. But once you see a heartbeat, it drops it to under 5%. So that's really nice to know. All right.
it was a strong heartbeat. So
Yeah.
I was happy.
All right, guys, we will see you then. We won't have class on Friday. Next class will be Monday, but we'll do lab if weather permitting. All right, we will see you guys hopefully in lab, weather permitting. But again, there's nobody panic over coming into lab at your own risk. Stay off the roads if it's really dangerous, unless you're highly skilled or whatever. All right, talk to you later.